Hello everybody and welcome. I'm very excited to be here with you today at the very first O3D Con. My name is Luis Mpe. I've been making games professionally for almost 20 years. I've been working on what is now 3D, and in particular I've been developing Script Canvas in order to make game development fun, fast, and efficient. I'm very excited to get started with today's workshop. We're going to dive a little bit into Script Canvas, a bit of an introduction, and we'll use it to make some game concepts and then try to bring something interesting on screen for us to play. So here's the plan. Before we dive into it, I'd like to quickly review some of the key concepts in O3D. If you have used O3D before, these concepts will be familiar, but if you're new and just getting started with O3D, I hope this helps you navigate this workshop with ease. So as I mentioned before, we're going to go over some key concepts. O3D is based on an entity component system. This means that we can build complex objects and hierarchies of objects using what we call entities, which is a container of sorts, and that container may have optional components. These components bring in the functionality, behaviors, and looks of your game elements and game objects. Elements in O3D are made of entities and components. We can start seeing a scene like this one, in which we have submarine, we have a light, and we have different elements that make up the scene. In this scene, the submarine is actually made up of four entities. It has the submarine itself, which is the one we see here. It has a valve, a light, and a propeller. If we look then at the components that make up the submarine entity, we see that it has a mesh, a material, and a transform. The transform component will be there by default for all entities, but the mesh and the material were components that I added so that I could specify the geometry and the materials that make up the submarine. Similarly, if we were to click on the light entity of this hierarchy, we see that it has a spotlight assigned to it, and that's the spotlight you see there in the image. Since we're going to be talking about Script Canvas, it's worth to mention that Script Canvas itself is a component. So any entity that you want or you wish to give behaviors to, you can assign a Script Canvas component on it, and that will allow us to begin crafting our behaviors and how we want our entities to behave. Now we're going to switch into O3D, where I'm going to give you a short tour of the Script Canvas editor interface. So here we have the O3D editor open. We have the scene that we were previously talking about open and ready, and we have many ways to open the Script Canvas editor. We can go here into the toolbar and press the Script Canvas option. In the tools menu, we have a Script Canvas option as well, or you can go onto the component and there's a way to open from there as well. Small difference, if you open the editor by itself, no graph is open for you. Let's say we open from the component, it will automatically create a graph and have it ready for you to author. Once you save this, it will assign it to the component and you will good to go. Our first stop on the tour is the node palette. This is the library of all the functionality that Script Canvas can give you within O3D. You can find this on the left side. It has the ability to search. You can search, let's say you want to search the light option. You will find everything related to light. And you can as well browse as you need. And we use it by drag and dropping from the node palette into the canvas, which brings me to the canvas. The canvas is the workspace. This is where we will actually author our behaviors, author our game scripts, author our logic, and interact with other systems. There are many options for working within the canvas that we will see as we go through the workshop. Next, in our next stop is the variable manager. As with any programming language, you might want to store data at some point. You want to store different types of data to do different operations. So here you will be able to create variables. You can give them a name. They support any alphanumeric number. We will go more in depth on the variable manager in a little while because it is very important to the scripts that we will be creating. Below it, you can find a node inspector. This gives you additional options that you might want to configure for not only variables, but the nodes themselves as well. So we will see it as we're developing. It will be handy. Finally, I want to talk about the graph validation panel at the bottom. Whenever there's a graph that may have a problem, you will get errors or warnings so you can rectify them. One common warning that you might receive is that you have nodes that are not connected to anything. This is useful so that you can come back and clean your graphs and make sure they don't have information they don't need. And for now, that will be all we're going to see, as most of the stuff we'll use is within these options, but there are more that you will be able to discover as you start using script canvas yourself. The next important concept has to do with the way scripts communicate. Auth3D uses an event mechanism for most of its operations. This is important because it allows us to have a decentralized approach to building games. It also allows us to send messages and data from one entity or script to another, one entity to many, or within its own components. As an example, the UI text input field has a method called setText, and while it looks like a method, underneath the hood it's actually sending an event saying, hey, I want you to set text, and this allows us to send it to any entity that may have a text field on it, and it will set the text. On the other hand, once the input field changes, the text changes, it will send out an event saying on text input change. This allows you to handle that case and do something like, in this case, print it to the console log. Perhaps you can use it to populate a leaderboard or do a logging. Whichever service you're using, this will allow you to send that data. Next, we're going to talk about variables and component properties. This is something we'll use a lot during this workshop, and that's why it is important that we cover it in a little more detail than most things. We start with a variable manager. We saw it briefly during our tour, but we're going to go a bit deeper now. When you create a variable, you have certain options. The first one being the name. You can name a variable, like we said, any alphanumeric value. You can even have spaces. It will have a type. This is any supported type. And by supported type, this could also mean types that your programmers have exposed for your game. Then we have the default value. This is the starting value of your variable. However, this is only used when the initial value field is set to from graph. More on this in a moment. Scope, this is used by functions, and functions is not something we will cover in this workshop. It's a bit more advanced, so we'll leave that for a different opportunity. And then finally, initial value. This has two options. It can be from graph or from component. When we use from graph, that means that we will use the value provided in the default value. So in the case of a value in this image, the value will be 1, 2, 3, or 123. And the value of my text will be hello world. Entity IDs don't have a default value because by default they will be invalid, and we have to set their value some other way. Finally, from component, this means that it will use the value specified on the component's property. So if we go back and select the entity that has a script canvas component, those variables that you marked as from component will be visible, and you will be able to override them on an instance per instance basis. So that covers the key concepts that I wanted to talk about, and we're ready to get started. So we're going to begin by adding some ability to control and apply movement to the submarine we saw in our initial scene. To do this, there are 5 steps we need to take. The first one will be to define the input bindings. This is a way to handle the input, whether it's from the keyboard, gamepad, joystick, or touch devices perhaps, and allow our scripts to react to them. Next, we will apply the input component to the entity that will be able to handle those events. Then we will apply a script canvas component on which we'll make a new script canvas graph. And finally, we'll handle the input events and we'll apply movement as a result. We'll start by creating our input bindings. So we'll go to the tool called Asset Editor and we'll select the input bindings asset type. In this asset type, we are going to create, start with one event, which we'll use to handle forwards and backwards movement. I will call this event forward for simplicity, and we will bind it to our standard keyboard mapping for movement. So we will set W to be our forward key, and we will set S to be our backwards key. Very importantly, on the backwards, we will change the event value multiplier from 1 to -1. This will allow us to determine if we're going forwards or back mathematically, which simplifies the construction of our script canvas graphs. Similarly, we will do the same for strafing, moving left to right. we will create a new event, we'll call it strafe, and we will apply the keyword bindings for A and D. Just as we did before, we will set A to be -1 on the multiplier. This way that means left, and D will be 1. So this will right. We save our asset as summary and controls. Now we are ready to go back to our entity, the summary entity, and add the input component on it. We apply summary and controls, we find it, and we're good to go. Now this entity is able to handle input events. Next step, we will add a script canvas graph. This will allow us to start creating those behaviors. So recall the script canvas editor. We will save our newly created graph as in a new folder for the summary. Let's call it submarine controls. And we are ready to start authoring it. So we'll begin with onGraph start. This is called anytime an entity that has a script canvas graph gets activated and starts operating, that node will execute. We will connect this to an input handler node, which is our intersection, it's our interface to the input system. We will handle the forward event because it's the one we defined previously. And we will also connect a second event that we will use to handle strafe. We'll begin by authoring just forward movement for simplicity, and then we'll go from there. Okay, so once you have your input held, the forward input held, we will get the world transform of the entity. This is the world transform of the summary in this case. There we will extract the forward vector, which we will use to mathematically move our summary forward. Now we need to move with some speed, so I'm creating a variable called speed that we will want to scale accordingly every frame. To do this, we want to track the delta time between frames. So we will add an onTick event, and we're going to drag this variable onto the delta time slot. This creates a reference to that variable, and whenever that event, the tick event fires, that variable will be updated with the value of the delta time. And we'll add a comment. So we remember every time we come to this graph and read it again, we will know what this is doing. Also, if someone you work with or you're collaborating with comes to read your graph, they will also understand what's going on. So now that we have our forward vector, we will want to restructure the logic a little bit, because we want to multiply the delta time by the speed. This will scale the speed per frame so that the movement appears to be very smooth. And after that, now we can get the forward vector, which we will scale to this speed multiplier. Finally, now we will get the world translation. This is the position vector for the entity, and we'll add these two vectors together. The end result will be a new position, which we will set as the new world translation for this entity. So this should give us some amount of forward motion. So quick review of our logic, make sure that it's correct, that we didn't miss anything, that nothing stands out. It looks correct. We save our graph and we will try it. Spoiler, I know there's a mistake, so there's no movement happening. So let's go back to our graph and let's see if we can spot the mistake. Okay, we review quickly our graph. Nothing stands out yet. Oh, there it is. We did not set a default value on the speed, so the speed was 0. So naturally, 0 times 0 is a big fat 0. Also, we want to set it to from component so that we can override this value per instance. So now we have some forward motion at a speed of 5. Okay, now that we have this forward motion, we can apply backwards motion. And because we use the multiplier, we can simply add this multiplication in to our previous multiply node. And now when we press that input for backwards, we get backwards motion. We're basically multiplying that speed by -1, negating the trajectory of our submarine. And now having forward motion, lateral motion, strafing is pretty much the same. We will recreate the logic as we did before, and we will, rather than use the get forward vector, we will use the get right vector, and the rest of the logic will remain the same. I made a mistake there. I had copy pasted the forward vector, but what I wanted was the right, so I pressed Alt and clicked on the node, which destroyed it. And finally, we update our world translation with the new position vector, and we can give it a try. And there we go. We have lateral movement and forwards and backwards movement. Okay, so now that we have forwards and lateral motion, we're going to summarize, or to recap, we're going to go back and do the whole process again, but for vertical movement. So we go in and very quickly we'll add a new event, input binding called depth, and we'll assign the keys Q and E as our up and down keys. Having these applied, we'll save this asset. Don't forget to set the multiplier to -1 for up and 1 for down. Now we go back to our graph, and we are going to duplicate that whole series. So we're going to grab the motion, organize it a little bit with our automated organizing tools. You can press Control and right to select a whole row, and then Shift and up will align to the top, and then Shift and left will consolidate everything together nicely. And now that we copy pasted, we change our input to depth, and we'll swap get right to get up. Just a quick little organizing to make our graphs neat. There is a row connection there that we need to fix. There, we've deleted it, and looks good. Save it. Let's give it a try. Let's see how it went. Quick review. Oh, look, we missed actually adding the up. There we go. Up, down, well, down, up, forwards, left, right, backwards. Excellent. We've added all the movement. We now have user control on an entity. This is a great start. Okay, so now that we have movement, let's give our submarine a bit of life. It's very static at the moment, so we're going to go ahead and make the propeller spin. So we create a new graph, and every frame will be handling how the propeller rotates. So I'll create a variable called angle, which we will do a very similar process as before. We will increment the angle every frame by some amount using the delta time, so that it's a very smooth animation. So here I've added onto the delta time by setting it as the output field of that node, and I'm going to check if it's greater than 360 degrees. We'll set it back to 0. That way we get a nice continuous motion on our propeller. Having that, we will create a rotation quaternion from around the y-axis, which we will set to our angle that we previously calculated, and we need to connect it whether it's true or false that it's greater than 360, so that it's always creating this rotation. Finally, we do set local rotation quaternion, which will apply the rotation onto that entity. We'll save our script and call it Propeller, which is now on the script canvas component for the entity. And as we run it, we see that nothing really happened. So let's evaluate why. So let's see. Remember how before we were scaling the speed of our movement according to the delta time? Perhaps we need to apply a speed value to our rotation as well. So we're going to go and create a new variable, call it speed. Similar as before, now we will remember to give it a proper default value and to set it from components so it can be tweaked. We can play around the speed at which we want the propeller to move. And we'll do a bit of adjustment to the logic here. We will remove this add component, add node, and we'll replace it with a multiply and add node. This is a special node that just lets us multiply two values and then add to that result a third. It just consolidates the logic that we need to write. So we are multiplying our delta time by our speed and adding that to our angle, and then we're setting that value on the angle. That will be our end result, and now we're using it, and I think we're good to go. Let's give it a try. The propeller is moving, but very slowly. But because we are able to tweak the value, let's go and check what it is and set it to something bigger, something that we're sure to see. There we go. Now we have some movement. We very easily tweak the value to our liking, and our submarine now has a bit of dynamic elements to it. Okay, so far we've seen how we can easily use Script Canvas to interact with other systems in O3D, like the input system, and have our objects move in the world. We've given them some dynamic abilities so they look like they're animating. And we could take it further. We can go and apply certain speed values that are controlled by the actual speed of the submarine as it's moving. We could go a lot deeper. But I thought it'd be fun to have a change of dimension and move from the 3D world that we've been working in so far and move into a 2D world in a 3D space, which should be very interesting. We're going to create an animated sprite system, and we'll be using Script Canvas to do it all. There will be no native code written for this at all. We will begin by setting up our material properties so that we can render the sprites as you see in the image. We'll create a new Script Canvas graph that will allow the configuration of sprite animations and states, and then we'll cycle those frames, which is essentially just applying UV offsets and tiling parameters on the material. And finally, we will handle the input just as we did in the previous example and apply some movement to our sprites in the 3D world. We'll create a new entity, which we will call Sprite. We'll assign a mesh component, and we'll select a plain 1x1 mesh. Now we'll rotate it into facing the camera, so facing forward, so we rotate by 90 degrees, and we'll add a material. We'll generate the source material, and we'll give it a name that matches what we're building. In this case, a simple sprite, we'll call it Sprite, and we'll call the material Sprite 0. Now we will select to edit the source material. Now that we've edited the material, we'll change the preview visualization to plain so that it matches what we're building. And we'll select the texture of a sprite sheet that we have already prepared for this workshop. Notice that any arbitrary sprite sheet will be supported. We'll make sure that we can provide the dimensions we need. We'll begin by setting it to a cutout opacity, and we'll set center to 0. We'll do some real quick trial and error settings on the tiling so that we can get the visualization of a single frame. We'll disable shadows for now. Okay, now we have what looks like a sprite. In this case, we can begin to work on doing some of the more advanced behaviors that we'll want to do. We will now add a Script Canvas component, which we will use to drive all the animation and animation states. The first step will be to configure the Script Canvas graph to use the material system. So we'll create a string that will represent the material name, and we will save also a material assignment ID type we'll call material ID. This will allow us to reuse that material assignment ID throughout this graph. So when the graph starts, we will find the material assignment ID for the material, the name that we provided. So we drag that material variable into our name slot, and we assign it to the material ID that we want, where we want to save it. Next, we'll do some early configuration settings on the material. Mainly, we will make sure to override the property for the UV center and set it to 0, 0. We did this in the material. However, if we use a different material, it could be that those defaults do not match. So this will make sure that when this script runs, regardless of the material, it will be always correct. So now we'll begin doing the portions that will drive the animation in our sprite. We will store a variable that represents a current frame. We'll need a parameter that controls just how fast that animation takes place. Basically the time between frames. Now we'll create an array of vectors, vector 2, that we will use to define our animation ranges. You could think of this as animation states as well. And we'll do another array. This array will define the actual animation frames. We're choosing a vector 4 because the first two elements of the vector 4 will be the x, y coordinates of the sprite within its sprite sheet, and the z and w parameters will be the width and the height of the frame. This allows us to have different sized sprites for a given sprite. So now we will initialize our current frame by getting the animation ranges. This means we will need a variable that defines the active animation. So we'll create a new variable and we'll use that to initialize our current frame from the range from which the active animation is specified. The x parameter of our animation range will define the starting frame, so we will set that as our current frame. And this is a minimal initialization step we need to begin animating our sprite. We're at a good point. We're going to save it so we can continue to iterate on our script. Next, we're going to add a variable that will call number of frames. We will not use this one in the workshop, but it's a useful metric to have for debugging purposes or diagnostics. To do this, we use a getSize node and we pass in the animation frames container and we assign it to our number of frames number variable. It's always useful to add a comment that explains what this portion of logic is for. Okay, next we're going to do things that need to take place every frame while the game is running. So we'll drop an onTick node. This will execute every single frame and we're going to store that delta time into a variable. This will be useful so we can reuse that value throughout different portions of the graph. Very similar as we've done before, we will increment our frame time by the amount of that delta time. And if it is greater than our desired frame duration, then we will reset it. when the time is elapsed, it will signal that it's time to switch to the next frame. So we'll increment our current frame by 1. We will proceed to get the active frame, active range, animation range, in order to make sure that if we go beyond the last frame that this range specifies, we can cycle back to the initial frame. Finally, we will set the current frame to the desired frame within this range. This portion of the logic will control our frame advancement that will give us a smooth animation between frames. And now the next step is to actually perform the UV texture calculations that will offset the material into the desired frame of animation. So we'll start by getting from our frame array using the current frame variable that we have previously set up. We will get from the animation frames array the coordinates for our current frame within the sprite sheet. Remember, this will give us a vector 4, so we'll use extract properties to get access to those parameters, where x and y are the x and y coordinates of the sprite within the sprite sheet, and z and w are the width and the height for that frame. So now we need to divide the x coordinate by the size of the sprite sheet. So we'll add a new variable called sprite sheet width that we want the user to provide. And so we set it to from component, and we'll give it a default value, and we'll set a sprite sheet height, which also will be from component, and it will have a default value. Remember that by being from component, we will be able to override those values later to match the actual sprite sheet size. So now that we've divided, this gives us a normalized value on the sprite sheet itself, which we can use to set a property override float on the material. And we will override the uv.tileu parameter. And we need to assign the material assignment ID so that it knows to which material it needs to override. And now we're going to do the same for the rest of the parameters that we want to override on the material. So we're very quickly going to duplicate this logic, and we will change the values to match for the x and y ranges, connect all our data, connect all our executions, and finally we need to update also which properties we're changing, which will be offset u, offset v, tile u, tile v, and we'll document what we've done so far. And this is pretty much everything we need for a sprite system to actually work. So we can save this and go and test it. Now that we have finished authoring our script canvas graph, we will set it on the component for our entity, and we'll begin to customize its behavior. We initially set the material name to correspond to the LOD0 slot of our material component. Then we will update the width and size of the width and height of our sprite sheet. In this case, the 360 is 360 by 234. We will determine that our first animation state consists of 8 frames, so we'll put a range between 0 and 7, and we'll add 8 entries for each of our frames. We will then configure the coordinates within the sprite sheet, which I'm filling in here, as you can see. Now we can test and see if our sprite animation works. Something didn't quite work. Let's analyze very quickly what may have happened. And we see that there is a mistake. In fact, let's organize a bit. And the mistake is right here. I did not assign the current frame once we incremented it. So I'm going to do just that, add it as a result of our add node. And now every time we increment, that value will actually be stored in the variable. So we can save this graph. I can try it again. And there you have it. We have our first animation state drawing perfectly, and we have a very nice smooth animation of all our 8 frames. I want to point out that currently the sprite is a bit wide. We can change that by adding a non-uniform scale component, and then that allows us to change the X dimension of our sprite. It'll just make it look a little better. The next step will be, let's add a moving backwards. So we'll add another 8 frames for the backwards animation, and I will add another animation state. And now we can proceed to add some user input. So we'll add an on-graph start node, followed by an input handler. This should be familiar. We've done this before with our submarine. I have an input binding already set up, in which instead of forward, I call it y-axis. It's just easier to think like that in this context. When we press our forward direction, we're going to detect if the multiplier is greater than or less than 0. And that will tell us which direction we're traveling in, which we'll use to update that active animation variable to either 0 or 1, 0 being the walking towards the player animation, and 1 being walking away from the player. We'll reset the frame time back to 0 so the animation restarts from the beginning. Then we'll proceed to get the element of our animation range to make sure that if we go beyond the range, we can set it back to 0. Or, pardon, set it back to the start of that state. So this is the exact same logic we did when we initialized this script. We will just be doing it every time we press a key to make sure that when we make a change, we don't accidentally cycle beyond the frames that we need to for any given animation. So now we can test it out. We'll add our input component with our input binding as we did before. And this is where we're putting together the elements of the first part of this workshop with the second part of the workshop. Oh, we have a problem. Currently, the inputs are bound to the camera. So I'm going to go and disable the camera that is by default added to the level. And now when we press the keys, it no longer should try to move the camera around. And now we're going to just do a quick test to make sure that it's working. Remember, the active animation was exposed to from component. Setting it to 0, we see the default animation. We'll set it to 1, and we hope to see the backwards animation. Okay, that's working. That means that now when we press our keys, W and S, we should see exactly that. We can change the states of animation through keyboard inputs. So now we're going to add movement. First thing we'll do is we'll add a camera that is a child entity of our sprite so that it always follows it around. We'll align it so that it's looking towards our sprite. I think that looks good. Okay, so now the next step will be to put everything together. And we'll keep quickly on this one because it's the same thing we did for the submarine. So initially we'll have this setup that just defines the animation states. And we have now 4 states, one for forwards, back, left, and right. And they will just detect whether you're which input binding you are pressing, and we'll use the different multiplier to know whether you're moving left, right, up or down, or backwards and forwards. And then we will do the actual movement, which is the same logic we did before. We multiply our delta time by our speed. We get the entity forward. In this case, it's up because we rotated the plane. We get the world translation, we offset that vector, and we apply it. And then we can actually start moving within the world. And there you have it. We made a really fun sprite animation system that we can control and move around a 2D sprite in a 3D world. It's very exciting. But before we go, I think we have a little bit of time for a lightning round. We are going to add our little game a degree of polish so that it looks very nice. Start by changing the ground texture. Create a new material, save it out, edit it, change the texture to something that looks like dirt. Now we'll create a background entity with 1 layer for the first layer of our parallax scrolling background. Just as before, we'll assign a plane and we will add non-uniform scale to make it cover the background. Set it to 100. Now we'll do the same thing. We'll create a new material for it. We'll assign a background texture and we will set the tiling U parameter to match our scale, so 100. We'll set it to cutout so that the background is eliminated, and we'll give a full scale because it's a bit small. There we go, looks better now. Push it back. Now we can duplicate this layer, rename it to layer 1. We'll change the texture of our material, replace it with another one we have prepared. It's our mountainscape. Finally, we'll duplicate it again, and we will give this a cloudscape. Awesome. Now with offset, there you go. We'll try it. We have parallax background. But I think we can do better. I think we can add a bit of ambience. Let's go to a global sky and add the deferred fog component. We'll set it to make it look like there's a bit of a sandstorm. We'll tweak the parameters, just make it look as nice as you want it. It's a bit light. Let's tweak it again some more. There you go. Now it looks properly sandy. Excellent. And there you have it. Very quickly, very easily, we went from having something that looked pretty standard as a prototype or a testbed to something that is starting to look like a game. I hope you enjoyed today's workshop. ScriptCam provides access to all the major features in O3D. Today we learned how to interact with several of them: the input system, the event system, entities, materials, and it's only a small portion of all the things you can do. You can interact with the physics system, animation, audio, and more. If you're comfortable with C++, you can extend O3D and ScriptCanvas to suit the needs of your game. You can add new nodes, you can create new methods and expose data types that will help you make your own creations. Thank you so much for joining us today in this workshop. I had a lot of fun being here with you. I hope you did as well. If you have questions or you just want to come hang out, you can find the details on this website, o3d.org/community. You can find us usually in the hashtag SIG-content channel. I go by AMCN_LS. And you can just come in and ask questions about today's workshop, about scripting, about using O3D in general. We are all very excited of the great things we can accomplish, and we're eager to help you out. Thank you.